Does that one work? Is that one hooked up?
Yeah. Testing, 2, 3, 5.
All right, so we have Thanks.
Thank you very much. Hopefully you can hear me. And maybe I'll be able to even move around a little bit with this. I've been told that if I go to see Mike the Tiger, I shouldn't mention that I'm from the University of Georgia. So I'll do that. Get this in focus. Is that visible? Okay. Should we try to dim some lights, or?
Do we need the lights on for the video?
Okay. I see quite a few students here, and that's great because this talk is sort of a student-oriented talk. And please, it's also, I hope there'll be some audience participation, and please interrupt and ask questions, and or give answers, or whatever. Okay, first of all, our cast of characters. Here are the primes, starting off, 2, 3, 5, 7, 11, and so on. What are these numbers? These are numbers that are larger than 1 and cannot be factored into smaller whole numbers. Okay, there they are. Maybe you've heard of them before. You can see that after 2, all of these numbers are odd. In fact, in the beginning, it looks like you're getting all odd numbers. But you see 9 is missing, and 9 is missing because it's 3 times 3, and then 15 is missing because it's a composite number. It's 3 times 5. And slowly but surely, more and more, even odd numbers are beginning to be missing from the list. Like here we have both 25 and 27 missing, and so on. The first problem I'd like to present to you is sort of a silly one. Why isn't 1 considered a prime? Okay, I said it's a number larger than 1 that cannot be factored into smaller numbers. Well, 1 can't be factored into smaller numbers, so why do we have to put in this little asterisk about it being larger than 1? Why do we not allow 1 to be a prime number? Well, it's not actually that serious a reason. It's sort of a silly reason. It's because we'd like to say something. We wouldn't be able to say it if 1 was considered a prime. What we'd like to say is that every number is either a prime or uniquely factorable into primes. So take, for example, 10. 10 can be factored into primes, 2 times 5. But suppose you allowed 1 to be a prime. Then you could say 10 is also 1 times 2 times 5. Or you could say 10 is 1 times 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 2 times 5. In other words, there wouldn't be any limit to the number of 1s you could say, and so therefore numbers would not be uniquely factorable into primes. So because of that nastiness, we say, okay, 1, you're not allowed. You're not going to be called a prime. Okay. First problem, that's something we know. Okay. Not very deep. Maybe you've heard of the fundamental theorem of calculus. There's also a fundamental theorem of arithmetic. This says what I just said, that every positive integer is uniquely factorable into primes. In fact, on the last slide, I ruled out 1 from this. But in fact, you can even allow 1. It's an empty product. By convention, that empty products are 1. So this comes connected with the fundamental problem of arithmetic, which would be do it. In other words, given a large number, decide if it's a prime number or not, and if it's not a prime, factor it into primes. So let's try an example. Would somebody like to give me let's say a 3-digit number? Somebody call out a 3-digit number. 231. Okay. Now, given that integer 231, we'd like to know, is this a prime number or is it not a prime number? Well, it's divisible by 3. And if you divide 3 into it, you get 3 times 77. And then you can see that 77 is still a composite number, so we can factor it further and get 3 times 7 times 11. And that's the factorization of 231 into primes. Maybe I shouldn't push this too much further. It's pretty easy for you to give me a problem that I'm not going to be able to just do so easily. I call it the fundamental problem of arithmetic, and the reason it's a problem is it's not so easy to do. Small numbers like 231, I was lucky that you, okay, let's try one more. Somebody give me a bigger 3-digit number. 641? Is that what you said? 641. Okay, well, what do you think about that number? I think it's a prime number. Okay, so what I did here is I tried to divide that by the primes up to its square root, and none of them go. So it's a prime. Hopefully I'm right. And if you can embarrass me and give me a factorization of this, more power to you. I think it's a prime number. Okay, let's look at a bigger example. What I'd like to do is I'd like to take the number, a high power of 2, that's 2 to the 512 power, and add 1 to that. If I didn't add 1, and I ask you to find the prime factorization, you could say it's 2 times 2 times 2 times 2, 512 times. But I added 1 on, so you can't say that anymore. And so now the idea is, can you factor this? Now, this number has about 155 decimal digits. And for a long number of years, we knew a factor of the... Oh, you working out 641 up there? Is that what you're doing? What? 641. It's prime? Okay, great. Good. Confirmation. Good. We knew a 7-digit factor of this number. Here it is. 2,424,833. And we knew that the remaining 148-digit number was composite. We knew it was not prime. But we didn't know a factorization of it. And here is its factorization. Okay? This was found a few years back by this crew of people down at the bottom using a method suggested by the last person on the list, John Pollard, called the number field sieve. So there was a lot of effort that went into this, a lot of ingenuity that went into this. The people that factored this did not try every number up to this number here till they finally got it. They did not do that. It would take too long to do that. They used much fancier methods. Now, you could say, what's the use of this? Mathematicians hear that a lot. It's funny, no one ever says, what's the use of a poem? You know, they never challenge the poets. But mathematicians always seem to get challenged. Here's a headline from the New York Times from March 1994. There's an actual photocopied headline, "The Assault on," and then follows a 129-digit number. Now, this number is a bit shorter than that 148-digit number that I just showed you. But this number doesn't have any special properties, like the other number came from 2 to the 9th plus 1, and that was exploited to help factor it. And this number doesn't have any beautiful way it comes from it's just sort of a big random number, random looking number. And why should the New York Times have this headline? I mean, who cares that people are trying to factor this 129-digit number? In fact, it was factored a few weeks after this headline appeared. It was factored using the quadratic sieve method, a method that I helped develop. And the reason that this is interesting, and the reason that the New York Times should have a headline about it, is because there's an apparent asymmetry going on with this fundamental problem of arithmetic. It's easy to multiply. And if you have a computer, it's really, really easy to multiply. It's hard to factor. It's easy to put together. It's hard to tear apart. This asymmetry is the basis of prime number-based cryptography. This has become very important with all the work that people do on the internet now, where you buy things putting your credit card through the internet. The internet is not secure. It's easy to eavesdrop. It's easy to intercept other people's emails and stuff like that. So if you put your credit card through, you don't want some hacker in North Dakota picking up your credit card number and stealing your credit. So these things have to be encrypted. Cryptography is not just for big governments anymore, and not just for the military. It's for you and me. It's for everybody who does any kind of business on the internet. So the kind of cryptography that the internet uses is based upon this fundamental problem of arithmetic and this apparent asymmetry. There are many other uses of prime numbers and number theory. Here's a headline of an article that appeared in Business Week also in 1994. So a big feature of this article was the cryptography, but also many other uses of the subject. At the end of my talk, I'll tell you about a really strange and very real use of prime numbers that sounds like it should be on the X-Files. It's talking to aliens from space. Okay, so but that's at the end of my talk. Okay, let's ask some beginning questions about primes. So, for example, maybe the biggest prime we've seen so far in my lecture was the largest prime factor of that number 2 to the 9th plus 1. Does anyone remember what that was? Oh, okay. But it was a pretty big prime. So I can ask the question, are there very large primes? And he says, yeah, that number there was pretty large. In fact, it was, I think, 99 decimal digits. That's pretty large. Is that the largest prime that we know of? No. Here is the largest prime that we know of. It's also near a power of 2. It's 1 less than 2 raised to the power 3,021,377. It was found within the past year by Spence and Waltman. It is the largest number for which we actually know that it is prime. Let me ask another question. Are there arbitrarily large primes? Okay, are there arbitrarily large primes? So, I'll leave this up for a minute. The answer to that is yes. There are infinitely many primes. The primes go on forever. This very, very big prime here is not the largest prime ever. There are bigger primes, infinitely many bigger primes. The first person to prove this was Euclid, 2,300 years ago. And Euclid's proof was deceptively simple. He said, assume there are only finitely many primes. Assume the list is finite. Multiply all those primes together. Get a really, really big number. Add 1 to that really, really big number. And this new number, since it can be factorable into primes, well, it can't be factorable by any of the primes that you just used, because if you divide any one of the primes you just used into this really big number, you're going to leave a remainder of 1. So you have this really big number that doesn't have any prime factors. which is a violation of the fundamental theorem of arithmetic. And so this violation was created by assuming that the list of primes was finite. Actually, a friend of mine, Hendrik Lenstra at Berkeley, pointed out to me at one point that no one had actually proved that there are infinitely many composite numbers. Okay? These are the numbers that are not prime. I mean, he couldn't find it in any book. I mean, he looked, and he couldn't find anywhere a proof. There are infinitely many composite numbers. There are infinitely many primes, yes, but what about the other numbers, the composites? Now, maybe you can think of a proof yourself of this. But he came up with a really nice proof, which I want to share with you. He said, assume there are only finitely many composites. Okay, multiply them all together. Don't add one. Yeah, that's it. That's his proof. Okay. In the 1700s, Euler came up with another proof that there are infinitely many primes. And this is a sort of a strange proof. He proved that the sum of the reciprocals of all the primes is infinite. And so therefore, if there are only finitely many primes, the sum would have to, of course, be finite. But since the sum is infinite, there have to be infinitely many primes. Euler's proof was based on the divergence of the harmonic series, on the fact that the sum of the reciprocals of all the positive integers is infinite. Now, you might say that last statement is obvious. It's obvious that if you sum the reciprocals of all the positive integers, the result has to be infinity because there are infinitely many things. But in fact, if you haven't studied this yet in your classes, you should already know that it's possible to sum infinitely many things and get a finite sum. So, for example, even if you haven't taken any advanced courses in math, you know that the decimal for 1/9 is 0.1111 forever, which means that 1/9 is the infinite sum, 1/10, which comes from the first decimal place, plus 1/100th, which comes from the second decimal place, and so on. So 1/9 is represented as that infinite sum. And here's another infinite sum also. This one converges to pi squared over 6. We have the sum of the reciprocals of the squares. So even though there are infinitely many squares, the sum of the reciprocals is finite. This last fact was proved also by Euler. So Euler showed that unlike the squares and unlike the powers of 10, the primes have the property, they are so numerous that the sum of their reciprocals is infinity. So he not only shows infinitely many, but he shows that in some sense they're more common than the powers of 10 and they're more common than the squares. Okay, we'll come back to this idea of summing reciprocals in a second. Let's come to the next topic, twin primes. Okay, you look through the sequence of primes and occasionally you see two of them that are only 2 apart. Since primes after 2 have to be odd numbers, they can't get closer than 2 apart. Okay, so the closest 2 primes can ever get after the primes 2 and 3 is 2 apart. And we find these examples of primes that are 2 apart. A larger pair that I happen to know is 197 and 199. They're both primes, and they're just 2 apart. They're called twin primes. So we can ask the same kinds of questions about twin primes that we asked about primes. We can ask, are there very large twin primes? So people have gone and looked. And this is an example from earlier this year by Ballinger and Gallo. They found these 2 numbers, and if you check my arithmetic there, if you add 2 to the smaller number, you will get the larger number there. Okay? You agree? If you add 2 to the smaller number, you will get the... And also, both of these numbers are prime. I won't ask you to check that part. But they're both prime numbers. This is the largest known example of twin primes. Okay, the largest known example of twin primes. But is this the same idea as with primes? I mean, is there a largest pair of twin primes, or do they go on forever? I mean, okay, let's say now you're the researcher. You're thinking like Euclid, you're thinking like Lenstra, or whatever. What do you want to do? You want to multiply them all together, or what? I mean, do the twin primes go on forever? Well, we don't know the answer to that. This is an unsolved problem in mathematics. As simple as this problem is, we don't know the answer. People have studied this problem for at least a few hundred years, and we have no idea how to prove this. We have a conjecture. Our conjecture is that there are infinitely many, but we don't know how to prove that conjecture. Now, in the other direction, in 1919, a Norwegian mathematician, Brun, Viggo Brun, showed that the sum of the reciprocals of the primes that appear in twin prime pairs is finite. So maybe he was trying to do Euler's proof. He was going to try to show that the sum of the reciprocals is infinite, and therefore there are infinitely many. But in fact, his proof showed the opposite. The sum is finite. Now there are two ways that this sum could be finite. One way is that there are only finitely many terms. They stop at some point. Then, of course, Brun would be right. The other way it could be finite, it's sort of like the sum of the reciprocals of the squares or the powers of 10. It converges. We don't know which way. We don't know whether it's finite because it converges or finite because there are only finitely many terms. You might say, what's the use of that? I'll tell you an interesting use of that. That infinite sum, or perhaps finite sum, whatever that number is, it's now known in the literature as Brun's constant. And so it'd be nice to know what Brun's constant is to several decimal places. In fact, Tom Nicely, a mathematician at a small college in Virginia, at Lynchburg College, predicts that Brun's constant is approximately that number. Yes? Is there any upper bound? What? Is there any upper bound? Right. You can prove an upper bound rigorously of it, and the upper bound is something like 2.3. Okay? But then using various conjectures and lots of calculation, Nicely predicts that it'll be this. So this is not a theorem, but it involves a great deal of calculation. And in fact, you've probably heard of this calculation, even though you had never heard of twin primes before. And let me tell you why. Nicely was working on a bunch of computers at his college in various labs, using them in spare hours. And this was some years ago, just when the Pentium chip was coming online. And so at his college, they had some Pentium computers, and they had some pre-Pentium computers, some maybe 286s and 386s and 486s. And he found that he was very, very careful, very meticulous in his calculations. He was maybe a little skeptical that computers always tell the right answer. And he was duplicating some of his work. And he found that the results coming in were not exactly the same. They were like wrong in maybe the 10th decimal place or something. Now, the computers aren't supposed to make mistakes like that. They're supposed to, if you're doing it to 20 places, they're supposed to agree in the 10th place. They're not supposed to have an error. So he thought, maybe there's something wrong with my program. So he went and he checked his program. Nope, nothing wrong there. So then he finally discovered that the mistake was happening in the new computers, that the new computers were giving the wrong answer. And he discovered the famous flaw in the Pentium chip. He called up Intel. They were too busy making these commercials of people in these spacesuits and whatever. But they didn't care. They said, you know, no one will ever care about that. So it hit the internet and hit the newspapers, and it ended up costing Intel $475 million in write-offs to fix this bug that they should have fixed earlier when it was pointed out to them. And this was all done by somebody who was only interested in twin primes. Okay? So, unbelievable. Here's something else that we consider. We know that there are infinitely many primes. We can count how many there are up to x. And the standard notation for this is pi of x. So here pi doesn't necessarily mean 3.14159, whatever. It's just a letter, and this is the standard notation. Pi of x is the number of primes up to x. So for example, the number of primes up to 10, well, there are 4 primes up to 10, 2, 3, 5, and 7. And there are 25 primes up to 100. So you could ask the question, how hard is it to compute this function? So for example, I give you an x, you tell me how many primes are up to x. So I'll give you a really big x right now. Suppose I ask you, how many primes are there up to 10 to the 20? Anybody know? Quite a lot, right? This is exactly how many primes there are up to 10 to the 20. Exactly. Now this also took a lot of cleverness and hard work to do this. Obviously, well, maybe it's not obvious to you, but this answer is actually about 2 times 10 to the 18. Computers are very fast, but even though they're very fast, they can't count 2 times 10 to the 18 things. It takes too long to do that. Suppose they could count 1,000,000 things a second. Then they could count maybe 3 times 10 to the 13 things in a year. And so it would take maybe about 10 million years if they could count 1,000,000 things a second to get up to that number. He didn't do it by counting individual things. Okay? It was by a much more clever method. Now you might want to wonder, okay, so it's pretty hard to do. This is in fact the record calculation of pi of x. You might wonder, could you have predicted some number close to there that was actually with less work? Here's a calculation that doesn't take very long and doesn't take a lot of cleverness. I know you have a site license here for Mathematica, and you can ask Mathematica to compute this integral. In fact, there's even a function that Mathematica recognizes, which is this integral. It's the function capital L, lowercase I, bracket x, lie of x. And it'll tell you that, if you give it the right precision, that lie of 10 to the 20 is this number. Now you can see that this number in green at the bottom of the screen is not exactly equal to this number in purple at the top of the screen. Okay? Let's compare them. They're the same number of digits, just as long as each other. The two numbers begin, looks like, with the exact same first 10 digits. Exact same first, and then they, after that, in the last 9 digits, they get to be different. The number at the top of the screen, the one in purple, was really, really hard to compute. It took a lot of work. There was a whole paper in a journal describing how this was done. The number at the bottom of the screen, you can do yourself very easily. It takes a second on the computer. So is there a pattern going on here? Is there a theorem here? In fact, there is a theorem. This theorem was actually conjectured by the German mathematician Gauss when he was a teenager, staring at a table of primes. And he conjectured that if you took the ratio of the number of primes up to x and divided it by this integral, then that tends to 1 as x tends to infinity. Okay, so he was just saying the ratio of those two numbers. And so he just did this. I think the story goes he was 14 years old. He was staring at a table of primes, and he came up with this function as doing the count for him. Pretty nice, huh? Anyway, it wasn't proved by him. And Riemann tried to prove this in the mid-19th century. And Riemann, in fact, conjectured something even stronger than Gauss. Riemann conjectured sort of what we already saw on the last slide, that the difference between the two functions is really, really small, about square root of x. The difference between the two is about that the two should agree for about the first half of their digits, which what we saw that happen. This is not proved either. This is an unsolved problem. This Riemann hypothesis could be considered the most famous unsolved problem in mathematics right now. Gauss's original conjecture, though, was proved, which is a weaker statement. It was proved about 100 years later by Hadamard and de la Vallée-Poussin, independently in 1896. it's amazing how you can come up with unsolved problems concerning primes. So here, let's pretend, I'm sure this doesn't go for any of you, but suppose you happen to be bored right now. Okay? And you have a piece of paper in front of you and talks about primes. You write down some primes, there they are. Think you're going to start doodling. Okay? So here's the kind of doodling that I'm going to do. So what I'm going to do is I'm going to write down the gaps between these primes. Okay, the gap between 2 and 3 is 1, and then it's 2, and then it's 2, then it's 4, then it's 2, then it's 4, then it's 2, then it's 4, then it's 6, then it's 2, then it's 6, and whatever, and you get this. You notice they're all even numbers after the first one, which is what we expect because all the primes are odd after 2. Okay, and now what we're going to do is we're going to write down the gaps between the gaps, because we're just doodling. We like this gaps thing, okay? But we don't like negative numbers, so what we're going to do is I'm just going to do the absolute value of the gap. So the gap between 2 and 4 is 2, and the gap between 4 and 2 is also 2. And I'll continue this pattern here. And I get some other sequence, and then I do this again, and I get a bunch of zeros now, and then a 2 and a 2, and I do this again, and whatever, and I keep on.
There's a mistake.
A mistake.
Last two. Next to the last line.
Okay, thank you. Now, if you don't make mistakes, the question is, look at these ones here. Do those ones go on forever? I mean, does every row start with 1? Of course, I'm not counting the top row of the primes themselves. This has been checked by Andrew Lisko, who works for AT&T, for tens of millions of rows. And it always starts with 1. It's not proved. It's an unsolved problem. By just doodling with primes, it's not very hard to invent something that is an unsolved problem. Okay? Here's another one. This is known as Goldbach's conjecture. This dates to the 18th century. Goldbach wondered if every even number, starting with 4, is the sum of 2 primes. Okay, would somebody like to give me an even number below 100? 78. Okay, is 78 the sum of 2 primes? Can somebody do it? Great. It's 73 plus 5. In fact, you can do it in more than one way. It's also, does anyone know another way? 71 plus 7. And there are probably some other ways too. Okay, so Goldbach's right about 78. Okay, would somebody like to give me an even number between 100 and 200? What? 120. Can you write 120 as the sum of 2 primes? What?
Season's apologies.
103 plus 17, that works. I know another way. What? Is it the sum of twin primes? 59 and 61, that's great. 101 and 19. Or 113 plus 7. So on. So there are lots of ways to do this, and probably there are a few more. So Goldbach seems not only to be right, but really right, because I mean, the bigger you go with these even numbers, it seems like the more ways, there's more than one way to write it as a sum of 2 primes, lots of ways. This has been checked recently up to about 10 to the 14, and every even number up to that level is the sum of 2 primes. Okay, it's not been proved. It's an unsolved problem. And so you thought mathematicians were smart, huh? We're not so smart. We can't even solve simple things like that. Here's something else. This goes back to Fermat. We saw the number 2 to the 2 to the 9 plus 1 at the beginning of my talk. And Fermat conjectured that 2 to the 2 to the k plus 1 is always prime. This is actually of interest to high school geometry. In high school geometry, you learn things like ruler and compass constructions. And so, for example, you might have learned how to do a regular hexagon. And maybe if you were in an advanced class, you learned how to do a regular pentagon. Well, that's because 3 and 5 turn out to be primes. You can do those with straight edge and compass. Fermat said these numbers are always prime. It's true up to this one, the fifth one on the list, which is 2 to the 16 plus 1. And after this, every one we've examined, every single one we've examined past there is composite. So it looks like Fermat was way wrong on this. He conjectured they're always prime. He's right the first 5 cases, but he was wrong for every case we've examined after there. Now the trouble with this problem is that these numbers grow so darn fast. Each number is close to the square of the preceding one. And so each number is about twice as long as the preceding one. You saw how long, when we get down to 2 to the 2 to the 9 plus 1, how long that number is. So you can imagine how hard it was to prove that 2 to the 2 to the 22 plus 1 is a composite number. And it is. I believe 2 to the 2 to the 23 plus 1, we don't know the answer to that yet. Maybe Fermat was right about 2 to the 2 to the 23 plus 1. It's just too big to handle at this point in time. So here's another question. Are there infinitely many primes in this list? Or do the primes, is this the last prime in the list? We now conjecture that 65,537 is the largest of these primes. Okay, let's talk about communicating with space aliens. How in the world are you going to do that? Now, you could send radio signals. Radio signals travel a great distance through space. You could beam them at some star, maybe 5, 10, 15 light years away. Maybe a star where we've detected that there are planets. 5, 10, 15 years from now, our radio signal will arrive. Will the beings living there receive our signals? Well, if they're a primitive culture and they haven't invented radio, no. If they're an advanced culture, then probably they'll get these signals. How will they be able to decipher them? Will they know English? I don't think so. Some years ago, a Dutch mathematician and philosopher invented a language based upon the principles of pure logic. This is Hans Freudenthal. And here's the name of his language was Linkos. And here is an example of a passage written in Linkos. I'm not exactly sure how this would be sent by radio, but it was an attempt at making a language. This was a real attempt by a real person to make a language that should be understandable to beings from other planets. And you can tell some Latin roots in here, perhaps. In fact, the book that I copied this out of, it said actually that this passage was actually telling the story about how men and women make babies. I'm not kidding you. It really said that. So this is really an X-rated slide here. But you can see some like HOM and FEM and stuff like this. So maybe we can even start maybe trying to understand it. Okay, but let's not. Because there's a better idea around. And the better idea was invented by an astronomer named Frank Drake. And Frank Drake had this better idea. He wanted to send pictures. He wanted to send photographs to other planets. Now, how in the world are you going to do that? Did they get cable up there? I don't think so. So to illustrate his idea, let's say we wanted to send a very simple picture to another planet. So the picture is of a square or a diamond, and here down at the bottom of the rectangle, you see the counting numbers 1 through 5 written in binary. And say that's the picture you want to send. How are you going to do that? Well, what you're going to do is you're going to send a sequence of dots and dashes. Okay? You find this frequency that's going to go far through the universe, aim it at some planet, some star system, and you send dots and dashes. Here is a sequence of dots and dashes. I've represented them by zeros and ones. And the length of the sequence is 55. Now what you do is you repeat this over and over again. So you send it, pause a little bit, send it, pause a little bit, send it, pause a little bit, and so on. Now, if there's someone at the other end receiving this, what do they see? They see something repetitive, over and over again, the same thing. Obviously, this is not noise. This is not static. This is supposed to mean something. Okay? What does it mean? Can we decipher it? Okay. How many dots and dashes did I say there were? 55. Is 55 a prime number or a composite number? It is a composite number. What is its prime? It's pretty easy to factor, right? It's 5 times 11. Well, if you have 55 things and 55 is 5 times 11, that means you could arrange those 55 things in a pattern, in a rectangle. In fact, there are 2 ways to do it. You could arrange it in 5 rows of 11 each, or 11 rows of 5 each. Well, okay, here are the 2 ways. One of the ways doesn't mean anything. The other way does. Look at the tall one here. Let me highlight to you where the ones appear in the picture. There are some ones at the top in the shape of a diamond. And then at the bottom of the picture, you see the actual binary numbers, 1 through 5, that we saw at the bottom of the screen. So here is a very, very simple example of how you might send a picture. In fact, if you did this instead of using a TV screen with 55 pixels, suppose you sent a TV screen with, close to 1 million pixels. Okay? Maybe something like TV screens we use today. And you arrange the number of pixels to be the product of 2 primes, so that you can arrange the pixels in a rectangle. And then you can send an actual photograph of Mike the Tiger, for example, right? And then in the next screen, you could show Mike the Tiger again, a little bit different. And then a little bit, you could send a movie. You could send a whole movie. Okay? So this is all done via prime numbers. Here is a picture that has actually been sent. This was sent out of the radio telescope in Puerto Rico at Arecibo. And the dots and dashes are arranged in this rectangle. This was done with 1,679 dots and dashes. And that is the product of the primes 23 and 73. And it can be arranged into this tall rectangle. And supposedly, this picture here is supposed to be decipherable to space aliens. To my taste, this is much too complicated. And it would sort of be like trying to decipher hieroglyphics without having the Rosetta Stone to do so. The top of the screen is supposed to involve the numbers 1 to 10 written in binary. I don't know, maybe that would be decipherable. Then each row or maybe it's each column here, stands for the atomic numbers of the most plentiful elements on the planet Earth, namely hydrogen, carbon, nitrogen, oxygen, and phosphorus. Or maybe those are the most important elements for life. I guess that's what they are. And then we have here formulas for sugars and bases and nucleotides of DNA. So we're telling them what we're made of. I don't know if it's such a wise idea. Anyway, here is the number of nucleotides in DNA. Here is a double helix design. Here is a picture of a person. Here is the height of a human being. There's a number that appears here, and this is supposed to be, goes from there to there. How are we going to tell them the height? Do they use metric? How are we going to tell them our height? Well, the message is sent on a certain wavelength. There's your measure, how long that wavelength is. Okay, and how many of those waves? Okay, so you can even start measuring things. This number over here is supposed to be the human population on Earth. Here we see our planetary system, our solar system. Here's the sun. Here are the 9 planets. You see the Earth, being the third rock from the sun, has a slightly different position than all the others to show them exactly where we live. And here is the radio telescope at Arecibo, and here's the diameter of the telescope down at the bottom. So here is what has been sent. I think it's too complicated, but anyway, this is what's sent. Maybe a committee designed it. Maybe that's what happened. So everyone had their own idea of what ought to be done. So actually, I don't know if you saw the movie Contact, but this is discussed in that movie and also in the book written by Carl Sagan. And the ironic thing is that here, prime numbers are being used in such a way to make communication possible, even between two civilizations that don't even share anything other than the most fundamental thing of all, prime numbers. Yet on the other hand, the other application of prime numbers that we saw was to make communication hard to decipher for cryptography. So at the same time, prime numbers are used for this completely opposite thing. So thank you very much for your attention. That's it.
Are there any questions? Comments?
Any answers?
Okay, well, we'll be here, same room, 3 o'clock tomorrow afternoon. Hope to see you then.
In this lecture, and I don't have too many amusing stories to tell about him, but I'd like to say a little bit about him as a teacher. When Robert Perlis met me at the airport on Monday, he asked me who my thesis advisor was, and I I said who it was, and we talked about him for a little bit. But actually, I met Paul Erdős a few years after I got my degree, and then my real education began. If you're a graduate student now, you might think that, wow, you're learning all this stuff. But really, you keep learning throughout your whole life. And when I met Erdős is when I really, thinking back, I probably knew before I met him only about 10% of what I know now. And so he is really an extraordinary teacher and a very extraordinary person. This photograph of him was taken perhaps about 4 years ago at a meeting in DeKalb, Illinois, an AMS meeting. And I remember one story that happened at this meeting. I mean, just to give you an idea of his sense of humor, which was a little bit weird, and some of his friends' sense of humor. He was giving a lecture at this meeting, and he was trying to remember the name of René Descartes. And he couldn't remember his name. And he said, you know, the guy that invented analytic geometry. And somebody shouted out from the audience, Descartes. He said, oh yeah, that's right, thank you. If I could only figure out what goes on in the brain when you can't remember, but you can remember, and whatever the connections that the brain makes, surely I would get the Nobel Prize for physiology. And then his friend John Selfridge shouted out from the audience, that's all right, so long as you don't remember the name Alzheimer's. And so this was sort of an insulting joke, right? And Erdős thought this was the funniest thing he ever heard in his life. And he started telling the story wherever he went after that about what Selfridge had said. So very, very peculiar things struck him as very funny. I think, that he's famous in lots of ways. I know he visited here to LSU probably lots of times. I don't know if he spoke much about number theory here, because he had many different things to talk about. And he often talked about graph theory and the probabilistic method and combinatorics, and he worked in approximation theory. But of his 1,500 papers, approximately half of them were in number theory, including his very first papers, and including, I think, his most famous papers are in the subject of number theory. Probably his most famous paper of all was concerning the prime numbers. I spoke about the prime numbers yesterday, and so the first part of my talk will be a little bit of review of what I said yesterday. But if you weren't here yesterday, then it won't be a review. Anyway, the story begins about 200 years ago. Gauss, as a teenager, was staring at a table of primes. They didn't have computers back then. They didn't have extensive tables. Maybe it went up to about 10,000. Okay? And he was looking at the primes in this table, and what did he notice? Well, he noticed that they thin out. Okay, so big deal. Anyone can notice that. But then what he tried to do is he tried to predict the rate at which they were thinning out. Well, that's pretty hard to do because they're erratic. Okay, sometimes there's a big gap, sometimes there's a small gap. They don't seem to thin out in any regular way. So what he did is he started counting up in intervals of 100 to see if he could smooth out the irregularities and try to detect some sort of law for the thinning out of the primes. And in fact, what he decided was that near a number n, it seemed like the probability that a number is prime is about 1 over log n, 1 over the natural log of n. So what that means is that in an interval of length 100 near n, you might expect 100 divided by log n primes to exist in that interval. So the next step was to do a Riemann sum, even though this was 60 years before Riemann. And so what Gauss said was that, therefore, we should expect the number of primes up to some number x to be this sum, 1 over log 2 plus 1 over log 3, and so on, up to 1 over log x. And that's a Riemann sum for a certain integral. And is that better? And so he predicted that the number of primes up to x should be approximately given by that formula. And here's an example of how right on the money he was. I gave this example yesterday as well. If you count the exact number of primes up to 10 to the 20, a very difficult computation indeed. This was done by Delaglease. He found this many primes. This is about 2 times 10 to the 18 primes. If you compute this integral, this definite integral of dt over log t up from 2 to 10 to the 20th, you get this number. And you'll notice that the two numbers agree to a very, very high precision, to the first 10 significant digits. So Gauss's guess as a teenager staring at the table of primes is absolutely tremendous. So what Gauss was conjecturing was that if you take this integral and divide it by pi of x being the number of primes up to x, that the ratio tends to 1. In 1859, Riemann made a stronger conjecture, essentially illustrating that right-on-the-money estimate that we saw in the previous slide, showing that the difference between this integral and pi of x is bounded by something near square root of x. This is still not proved, Riemann's hypothesis. And in fact, the Riemann hypothesis is perhaps the most, as I said yesterday, the most famous unsolved problem in mathematics. Someone came up to me yesterday after my talk and said, I thought the Riemann hypothesis had to do with zeros of the Riemann zeta function. That's the usual way it's stated. It's stated in terms of this particular function of the letter s, the series, as you remember from calculus or advanced calculus, it converges if s is a number that's larger than 1, and it diverges if s is equal to 1 or smaller than 1. If you think of s as a complex variable, this converges for the same reason if the real part of s is greater than 1, and it diverges if the real part of s is not greater than 1. As in the half-plane real part of s greater than 1, this is an analytic function. It can be continued to the entire complex plane as a meromorphic function with a single pole at s equal 1. And the Riemann hypothesis is usually stated that this analytic function has all of its zeros that have real part positive on the line real part equal to half. But it's equivalent to what I said on the previous slide, namely that Gauss's teenage conjecture gives a right-on-the-money approximation to the number of primes up to x. Now, what I'm telling you here, I'm not going to get into the details of this, but some amazing history of the problem of estimating pi of x, the number of primes up to x. It was conjectured in the 1790s by Gauss that this logarithmic integral is a good approximation. In the mid-1900s, Chebyshev had some important contributions to this, and Riemann proved it modulo his hypothesis. In the 1890s, Gauss's original conjecture was proved along the lines laid out by Riemann using complex analysis. And this became such an interesting thing for